Good morrow, fellow humans. My name is Sean Crowley and I am obsessed with infinity. So join me as I attempt to unpick the infinities of what is. When it comes down to it, a digital system can only ever at best be considered a description of an analog continuum, such as infinity or, as many would argue, reality. Time, too, might also fall within this category, though this would again depend on what time actually is. But even if time is a continuum, what's the issue with describing it as a series of points? Take, for example, the simple equation 10 divided by 3. Of course, when we do this, we get the answer 3 with an infinite of recurring 3's following the decimal. Nothing particularly peculiar about that. But what happens when we reverse the equation? Instead, we end up with a 9 followed by an infinite of reoccurring 9's. So what happened? What was lost? The reason for this is that infinity is not a number, it's an idea, and a fairly abstract one at that. The use of infinity in both mathematics and cosmology can of course be extremely useful, especially when attempting to describe events like the Big Bang. But just because the vast majority of science is built upon mathematics doesn't mean that mathematics is itself a science. In fact, mathematics is much more often akin to an art than a science. For just as mathematics can convey meaningful insights into the truths of our world, so too can great poetry. And though both mathematics and poetry have an ability to describe their truths with a degree of subtlety and fine-tooth precision beyond the abilities of the other, both are similarly limited by their very nature of being digital languages. These are linguistic and numeric structures born of our own creativity. And it is due to this origin that each language's primary service shall always be to serve humanity's intuition rather than offering up any non-fallible truths about reality. At our day-to-day scale of macroscopic interactions, mathematics, like any language, works perfectly well. It describes the world we encounter. One apple plus another apple is clearly 2 apples. But in order for this system to continue to hold up, we must continue to contain our descriptions to the realms of subjectively finite structures. Yes, we may now have 2 apples, but where in reality does one apple end and the next one start? Now, that might sound like a silly question, but once we start pushing into the atomic structures of each apple, those borders start appearing far less determined. Think of how it is when driving through the mountains as we climb up into the clouds. When we arrive at the top, what we once saw as a clearly defined edge of the cloud becomes revealed as nothing more than just a haze of poor weather, a borderless fog of mist. Apples, and even the atoms which make up their structure, are themselves no more defined than that weather, And so, in order to render the digital language of mathematics capable of describing what it finds within these fluid edges of our material world, we have allowed for a very human level of creativity to enter into its practice. In mathematics, if we wish, we can just say that something exists, like an apple, use it as a rule and just see what happens. If the rule causes contrary results, then we can either abandon the rule, or we can expand the rule to state that we must simply avoid the aspect that caused the contradiction. In other words, mathematics has evolved alongside humanity, receiving the malleability prone to all of humanity's tools. And so, it has been this malleable tool, limited by its digital nature and obscured by the perspectives of humanity, that we have long used when feeling out the shapes of the world around us. Similar to how a bat will use its echolocation to locate obstacles within its environment, we measure our universe by sending out our equivalent in the equations, which we then follow in patience, hoping that we might one day hit upon some new wall. Now, clearly it's not as simple as all that. And mathematics has definitely proven itself as an extremely useful tool in the navigation of our universe. But we have to acknowledge that, just as it is with the bat, our successes will only ever reveal truths that have fallen within the direction and scope of our tools. Ultimately, we can never know what aspects of reality that our method has lost in its translation. And the nature of infinity is a prime example of this. Mathematics, broadly speaking, defines two types of infinity: countable infinity and uncountable infinity. These were originally described by Aristotle in the 4th century BC. But it wasn't until mathematician Georg Cantor got involved in the 19th century that our current understanding of mathematical infinities really took shape. Cantor's genius went largely unrecognised in his time, with his ideas receiving widespread criticism. And it has long been thought that it was this professional rejection, along with the mind-bending nature of infinity, that led to his spiralling depression and intermittent institutionalizations. But what Cantor was the first to understand was how the mathematical infinities relate to one another, thus giving us the ability to calculate infinities as sets by giving them cool names like Aleph Null, Omega, or even better, Big Omega. Using these sets, we could now do number-like calculations with infinities, like infinity plus infinity equals infinity, or infinity minus infinity. Well, actually, you break things if you do that, but you get the idea. Infinities acting like numbers. Mathematicians tend to enjoy grouping things together. In fact, that's the very basis for what we call number theory. In our system of numbers, we have what's referred to as the integers. These are simply the natural numbers from 1 to infinity and their negative counterparts, -1 to -infinity. Beyond the integers are the rationals, or more commonly known to us as the decimals or fractions. Now, these can be finitely bound fractions like 0.5, or they can be infinitely repeating patterns such as 0.333 recurring or 0.123123123 recurring. But together, the integers and the rationals make up all the numbers that are found in the countable infinities. But it's the uncountable infinities where things get a little bit more interesting. Here enter the irrationals. In textbooks, irrational numbers are usually described quite plainly as a number that can't be expressed as a ratio of any two integers. But put more interestingly, irrationals are the infinities that lay between the infinities. These are numbers like pi, which, unlike the rationals, doesn't have its thread of decimals repeating off into some cyclical pattern, but rather a never-ending, infinite randomness. A randomness that is so freakish that it tends to break any equation it enters. In short, many of these numbers are considered transcendental, in that they literally transcend algebra. In 1888, whilst in correspondence with several philosophers, Georg Cantor proved that the vast majority of numbers that are out there are in fact transcendental. What this means is that the infinite set of transcendental numbers is bigger than the infinite set of both integers and rationals together. Now, there is every reason that this should sound odd to you, because after all, are there not infinite numbers in each category? And is infinity not infinite? How can one particular class of infinite numbers be considered a majority? Regardless of whether it was a 1 to 99% ratio, surely both are still an equal count of infinity. Here lies Cantor's brilliance. When we refer to the count of numbers within a set, we speak of their cardinality. In the case of the irrationals and transcendentals, their cardinality is actually larger than the cardinality of the whole numbers. In fact, there's such a big difference between the two sets that if we were to have an infinite vase filled with every single number that there could ever be, you would be next to guaranteed that your chosen number would be an irrational one. But where does this so-called cardinality come from? At a guess, we could suppose that the cardinality of just the odd numbers might be half of the whole numbers, since they occur only every second number. But this would be wrong, as both the odd and the whole numbers do in fact share the exact same cardinality. Thus they are considered the same sized infinity. The reason for this is that they can still be put in a one-to-one correspondence with one another. Meaning, I could pair the number 1 from the whole numbers with the number 1 from the odd numbers, and then the 2 with the 3 with the 5, the 4 with the 7, and so on into infinity. Every number, whether odd or natural, would always have a partner, no matter how long we continued the sequence. So when is this not the case? There is a little experiment that shows how irrationals are in fact different. That's quite easy, and it's only going to take us a moment, but it does clear up this whole bigger infinity debacle. So here it is. Imagine you were to create a spreadsheet with infinite columns and infinite rows, and then filled each row with a string of infinite numbers, including all the rationals and all the irrationals. Then, by our own rationality, we should have a spreadsheet that contains every real number, an infinite collection of infinitely long numbers. But then, if we take the number that's in cell A1, and regardless of what it is, just add to it the number 1, and then move diagonally down to B2, again adding 1, and then C3, and then continue this trend diagonally, infinitely down the page. What you will have done is created a number that didn't appear anywhere within the original set of infinite numbers. Even if you were to argue that this new number might be just hidden somewhere far, far down the list, it wouldn't be the case, because our new number will always differ by at least one digit wherever the diagonal intersection occurs. And so we have created a number that cannot be put into the same one-to-one correspondence as before. Thus, a larger infinity. And that's pretty much it. What Cantor proved was that there is an infinite array of these different-sized infinities, all stacked within each other, with the most ultimate being absolute infinity. For Cantor, this was an infinity so beyond comprehension that he equated it with God itself. Indeed, Cantor saw his entire insight as being ordained by the great Creator, claiming that the transfinites were real for the very reason that God has told me so. Though Cantor's work may have struggled to find its feet in its own time, it has since been referred to as the finest product of mathematical genius and one of the supreme achievements of purely intellectual human activity. But I, for one, have a small gripe. Not with Cantor directly, but with the mathematicians that followed, and the metaphor that they often used to describe his work. The linguistic error that has been encouraged the world over comes as a result of our tendency to describe things in terms of hierarchy. When describing the relations between these infinite sets, we often state that one infinity is larger than another, as I too have done here. Granted, even in textbooks, the word larger is more commonly bookended with quotation marks, revealing that silent nod to the audience and an acknowledgement of that blatant contradiction of terms. Since no infinity can ever be considered larger than another, as both are infinite. But this doesn't require us to deny the genius of Cantor, as what remains true is the relationships held between the infinite sets. These relationships show us how certain infinities can lay within one another, or even stranger, how infinities can happily reside within a figure that is finite. But beyond this, all infinities are still infinite. And so, because the language of sets is a language of relationships, we need to be very cautious about what metaphors we're choosing to use. For me, using a metaphor of scale, i.e. larger or smaller, seems entirely counter to the ideals of infinity. Perhaps one better option might be to use the spatial metaphor from a different perspective, such as when we're closer to a particular infinite set, we raise the resolution and thus cardinality goes up. In this way, sets of equal cardinality would not be deemed the same size but the same distance from the observer, or next to one another. Likewise, those with lower cardinalities are not smaller but further away. We need a metaphor that describes a density relevant to a finite segment of the infinite set, not one that declares knowledge of size total. This may be trivial, and it's likely that there are better options than those that I'm offering here. But as we shall continue to find, the metaphors we choose to use when considering infinities, be they mathematical or universal, can totally change the way we think about them. So for philosophical reasons, they must be highlighted. The way we talk is inevitably the way we think. And considering we are already using the digital languages of numbers and words to attempt descriptions of analog continuums. We just need to remind ourselves how this can prove problematic if left unchecked. Though if you think that mathematicians have a problematic take on the subject, physicists can be downright cavalier with their infinities, as we will get into in the next episode. We will get back to our discussion concerning the start and end of time and the infinities there within. For as Richard Feynman once put it, we have designed a method for sweeping them under the rug.
Thank you so much for listening. It's been great hearing from you in the comment section on our YouTube page. So hopefully we can continue to build this community, because they really do seem like an amazing bunch of people, and I'm very excited to be sharing this journey with you. I just wanted to quickly, because I haven't done this yet, I just wanted to quickly unfold my plans for this project. The idea is that I'm going to be unfolding a narrative, the unpicking of infinity, as I've said, over the next around 3 years. And I've separated those 3 years into 3 acts. The first act is going to be discussing primarily the ideas of physics. Following that will be consciousness. And then finally in the third act will be infinity itself. There's going to be many unfoldings and stories and dives into history that we'll do along the way. So I do hope that you'll join us for that. A quick shout out this week. Callum Woolcock, thank you very much. He gave up his time to assist me in making the visualizations for the YouTube episode this week. So a quick shout out to him. I encourage you all to go and check that out. Hopefully it's something that adds something to this project for you. A lot of work going into it, but I'm not going to take up any more of your time. Thank you so much for sticking around. Just going to say good morrow, and I hope you have a lovely week. All right, bye.